Welcome everyone. This video is a follow-up on the last lecture that I gave on the law of robustness for neural networks. It will actually be divided into two parts. In the first part, I will give you a crash course on tensors. And for this part, you don't need to know anything about the law of robustness for neural networks. It's just pure mathematics about tensors. And then I will move on to use those concepts and explain how they relate to neural networks and to the law of robustness. In this second part, it will be useful if you have seen the previous video, but not necessary either. I will remind you the necessary concept. Okay, with that being said, let's move on to the crash course on tensors. Okay, so let's start with a definition of what is a tensor product. So we are given two vectors. Let's call them U in H1. So H1 is a Hilbert space and V is in H2. H2 is some other Hilbert space. If you want, you can just think about RD, a finite d-dimensional Euclidean space. So given U and V in two Hilbert space, we define the rank 1 tensor U times V as the bilinear form which goes from H1 times H2 into R. And given two vector X and Y, it outputs the answer, which is U applied to X times V applied to Y. Okay? And here I think of U and V, I said that they are in the Hilbert space H1 and H2, and I identify them with their corresponding linear forms. Okay, using Rie's representation theorem, we know that the dual of a Hilbert space is isomorphic to the Hilbert space. So very simply, where U of X, again, U is a vector in H1, so it's also a linear form which goes from H1 to R, and it is defined by the inner product in H1. So U inner product with X in H1. Okay, and the reason that I define it like this, using linear forms and abstract Hilbert spaces, is that because then you can keep building it up like this. What do I mean exactly? Well, right now I have defined only the rank 1 tensor, U times V, but we are now going to define an entire space. So H times H2. Okay, the tensor product of the Hilbert space H1 with H2 is the linear span of rank 1. Oops, sorry about that. Of rank 1 tensors. Okay, so you take linear combinations of rank 1 tensors, and this is the space of H1 tensor product with H2. So just to be clear, if H1 and H2 are simply Euclidean spaces, then the tensor product is the set of bilinear forms, which is nothing but the set of matrices. But now you see you can take two matrices, for instance, and take the tensor product of two matrices. Okay, and that way you can build higher order tensors. Okay, so, but to do that, to build higher order tensor, I need to equip H1 tensor product with H2 with an inner product to make it a Hilbert space. So H1 times H2 is a linear span of rank 1 tensors equipped with the inner product, which is defined as follows. I'm only going to define the inner product on rank 1 tensors, and then it's going to be extended by linearity to any linear combination of rank 1 tensors, to all of H1 times H2. So what is the inner product? So the inner product of U tensor V, inner product with, let's say, X tensor Y, then this is by definition the inner product of U with X in H1 times the inner product of V with Y in H2. That's it. This is how you define tensor products. Okay, you just combine them, like you combine the linear form into bilinear forms by just multiplying each element. Okay, very, very simple object. Okay, so let's just see how it works out in the very simple case of taking RD and taking the tensor product many times. So example, what happens if you take RD, tensor product with RD, etc. Okay, you take this, let's say P times. This is what we're gonna call, this is a order P tensor. Okay, what does it look like? Well, T is a linear combination. So T is in this thing, which we're gonna call, RD tensor P times. So T is in RD to the P means that it's equal to a linear combination of rank 1 tensor. So it's a certain sum, let's say for L equals 1 to K of lambda K. And then what do we have? We have, okay, let me see how to denote this. U, let's say, UL1 times UPL. Okay, so it's just a linear combination of these things, and we can identify it. So RD tensor P times, this can be identified with maybe the classical computer science way to define tensor of order P is as array, P-dimensional arrays. Okay, so what do I mean? Like RDP. Okay, so let me see how to do this identification. So denote for a vector V of I is just V inner product with EI. Okay, so this is for V in RD. Okay, so Vi is just the i's coordinate of the vector V. So then you can identify this vector. So T, let me just see what I want to say. T, you can identify it with just applying T all with the value of T on all the canonical basis vectors. So what do I mean? Well, I simply mean, what do I mean? I simply mean the sum for L equals 1 to K of lambda K U1L applied to some basis vector EI1 and then times, etc., up to UPL applied to some vector, canonical basis vector EIP. And here I need to record all the indices, which is I1 up to IP. They range from 1 to D. Okay, so this is what you would more normally imagine. I mean, more classic, like in computer science, this is how a tensor of order P is described. It's just a big array with P indices, and each index range between, say, 1 and D. Okay, but it's perhaps nicer to think about it as a multilinear form. Okay, this is really what it is. Okay, in that notation, in terms of array, let's just see what the inner product corresponds to. So if you have T and S, two order P tensors with corresponding entries Ti1, etc., then you can just very easily check that the inner product is the sum for your range over all indices from I1 to IP between 1 and D. And you just sum the product of the corresponding entries. So Ti1 up to IP times Si1 up to IP. Okay, so this is the inner product. All right, which is nothing but the Euclidean structure on R to the dp. Okay, so at this point you might ask, okay, what did we do exactly? Okay, we have this multilinear form, but in fact they are just vectors in dimension R d to the p, d times p, and with the classical inner product on them. So what's the big deal? Well, the big deal is the rank structure. Okay, we have defined those objects starting with rank 1 tensors. And this is really the key. So what is the big deal? The big deal is that now we can equip this vector space with norms which are very different from the Euclidean norm. So let's do that. So what's special about the tensor product H1 times H2? So what's special is that we can equip it with very nice norms. So let's introduce a new definition, which is what's called a cross norm. So a cross norm is a norm on H1 times H2 such that, so norm such that if you apply the norm on a rank 1 tensor, okay, then the norm of this rank 1 tensor is nothing but the product of the norm of the corresponding element in their corresponding Hilbert space. So this should be equal to the norm of U in H1 times the norm of V in H2. This is the definition of a cross norm. So what's an example? Well, the Hilbert-Schmidt norm, the norm that comes from the Euclidean structure. So example, the norm of T, let's call it Hilbert-Schmidt, which is nothing but the square root of the inner product of T with itself. Okay, note, so let's just do it as a very, very simple exercise to make sure we have all the notation correct. So what do we want? We want the norm of U times V Hilbert-Schmidt. What is this? Okay, so it's square root of the inner product of UV times UV. But remember, what is the inner product? The inner product is nothing but the bilinear form evaluated on the corresponding vector. So this is equal to square root of U applied to U as a linear form times V applied to V as a linear form, and the corresponding inner product are in H1 and H2. But these are exactly the definition of the Hilbert-Schmidt norm in H1 and the Hilbert-Schmidt norm in H2. So this is a norm in H1 times the norm of V in H2. Okay, so the Euclidean norm coming from the Euclidean structure on tensors is a cross norm, and it's of course the uninteresting cross norm. What are interesting cross norms? Well, Grothendieck looked at two very interesting cross norms, the largest one and the smallest one. So more interesting. Here is a more interesting example. The largest cross norm. So what is the largest cross norm? I'm just going to write what it is and then tell you why it is the largest. So the largest is the norm of T, and I'm going to write a star. Okay, so I define the norm star as the largest possible cross norm, and there will be a reason why this comes with a star. It will be the dual of some other norm that we really like. So the largest cross norm is defined as the infimum of the sum of lambda L for L equal 1 to K, such that there exists UL and VL with T can be written as the sum of lambda L UL outer product VL or cross product VL, sum for L equals 1 to K, and of course the UL, so there exists unit norm UL and VL. Okay, so UL is of unit norm in its corresponding Hilbert space, and VL is of unit norm in its corresponding Hilbert space, and T is written as this rank 1 decomposition. Okay, and it's the infimum of the sum of all the lambda L's, such that this is true. So why is this the largest cross norm? Well, take any other norm, which is a cross norm, and apply it to T. Okay, so you have the norm of, and T can be written as a sum of L equals 1 to K of lambda L UL times VL. Then by the triangle inequality, the norm of T is smaller than the sum of the absolute value of lambda L times the norm of UL VL. But the norm of UL VL, because it's a cross norm, it's the norm of UL times the norm of VL, which is 1 because UL and VL are norm 1 vectors. Okay, so by the triangle inequality, this norm star is the largest norm. Okay, so again, by triangle inequality, norm star is the largest cross norm. Okay, very good. Notice that in the case of matrices, okay, so when your corresponding Hilbert spaces are just Euclidean space RD and RD, then again, the tensor product is simply matrices. And in that case, this largest cross norm, this norm star, is nothing but the sum of the eigenvalues or the sum of the singular values. Okay, so it's the nuclear norm in the case of matrices. And this is a generalization of the nuclear norm to more general tensors. Now, what is the smallest cross norm? The smallest cross norm is nothing but the dual of this norm star. So what is the dual? Well, the dual is the supremum over all tensor S such that the norm star is less than 1 of the inner product between T and S. This is a definition of the dual. Okay. And this is it's easy to see that this is the smallest one. Why is that again? Okay, it's easy. So it's easy to see that this is the smallest one. Why is that? Well, for any norm is the dual of some other norm, and cross norms, their dual are also cross norms. So here basically it's very simple. It's just that the supremum here is taken over the smallest possible set because the norm star is the largest cross norm. So this dual is clearly the smallest cross norm because it's the dual of the largest cross norm. But now let's try to see a little bit more what it looks like. So it's a supremum over all S. Then it's very easy to see. You see again by a very simple triangle inequality type inequality that the best I can do is simply to make S to be a tensor product or a rank 1 tensor. So in fact this is equal to the supremum over X and Y unit norm in the proper Hilbert space of T X times Y. Okay, this is it. And now again, you see, when you write it like that, I hope you recognize what is this norm in the case of matrices. It's nothing but the spectral norm. Okay, in this case, you're just maximizing on the sphere the bilinear form T, which is a matrix, which is nothing but the spectral norm, okay, the largest norm that you can get. And in this case, you even know that you can take X equal to Y, etc. All right. So these now equip the set H1 tensor product with H2, this vector space with a very interesting structure, whether you take the largest cross norm, which I'm going to refer to as a nuclear norm, or the spectral norm, which is its dual. So what do we know? So in the case of matrices, there are several facts which are very useful. So in the case of matrices, what do we know? So first of all, we know a relation. So in the case of matrices, there are a couple of facts about these norms that are very useful. So for instance, we know that the largest cross norm is not too much larger than the smallest cross norm. Namely, it's always smaller than D times the operator norm. Okay, why is that? Well, it's very simple. It's just because the nuclear norm is the sum of the eigenvalues or singular values, and smaller is there are only d of them, so it's more than d times the max of them, and the max of them is the operator norm. Okay, it's the spectral norm. So we know this inequality by eigen decomposition. But now for higher order tensors, we don't have this eigen decomposition. So what happens? Okay, what is the equivalent? We also know a very related fact, T can be decomposed in a sum of D rank 1 matrices. Okay, again, this comes from eigen decomposition. So eigen decomposition gives us a lot. It tells us that the largest cross norm is not too much bigger than the smallest cross norm, and also that you can decompose any matrix into a sum of D rank 1 matrices. So how do these facts generalize? That's what I'm going to tell you right now. These are very, very useful, quite generally, I think. Okay, so let's start with the second fact. So lemma 1. So if T is an order P tensor, then T can be written as a sum of D to the P minus 1 rank 1 tensors. So you see that when P is equal to 2, we recover that you can write it as a sum of D tensors. So this fact is actually completely trivial. I will explain why it's completely trivial. Now, a slightly less trivial fact is the fact that you can in fact write it as a sum of symmetric rank 1 tensors. Okay, so meaning instead of x times y, you will only have x times x. Of course, T might not be symmetric itself. So what does it mean? Well, it means that the action of T on any symmetric tensors can be mimicked by this sum of order D to the P minus 1 rank 1 symmetric tensor. So let me explain again. Moreover, there exists U, let me think, U1 up to UK with, so these are vectors in RD, right? With K, which is going to be equal to 2 to the P times D to the P minus 1. This K is not optimal, but it will allow us to have a simple proof. So there exist K vectors like this, such that for any X in RD, if you look at the action of T on X tensor P times, okay, so if you look at the action of T on a symmetric tensor, then this is in fact equal to the sum of U L tensor P times for L equals 1 to K times X to the P. And sorry, I need also some coefficient lambda L. So there exists U1 up to UK and lambda 1 up to lambda L in R real coefficients, such that this is true. Okay, so not only can you write a tensor of order P as a sum of D to the P minus 1 rank 1 tensors, in fact, if all you care about is the action on symmetric tensors, then you can write it as a sum of the same order of rank 1 symmetric tensors. Okay, so let's see a proof of this. So I claim that the first claim is completely trivial. Why is that? Well, I can just write it like this. T is the sum for I1 up to I P minus 1 between 1 and D. So I will just leave one index free of what? Of EI1 tensor product with etc. tensor product with EIP. So this is a canonical basis in RD times what vector will I see? Well, think of, again, now you think of T as an array, okay? A P by a d by d by d p times array. And what I'm going to do is that I'm going to fix a face, and then I have just one d-dimensional direction, like one direction left. And so what I'm going to do is that I'm just going to decompose the array into all of those vectors. Okay, and I have d to the p minus 1 of those. So what do I mean exactly? I mean t. And now here I look at the vector which is in the entries I1, etc., up to ip minus 1. And I left the last one free, let's say in MATLAB notations, like this. Okay. What does this mean? Okay. It means if I look at the entry I1, oh sorry, it was IP minus 1 here. If I look at the entry I1 up to IP, okay, so on the left hand side, the entry I1 up to IP, it's the same thing as taking the inner product of T with, T, let me just remind you this, T I1 up to IP, it's nothing but the inner product of T with E I1, tensor product, etc., tensor product EIP. Okay, so when I take the tensor product with EI1 up to EIP on the right hand side, the only thing which is going to survive is the term which in the sum which corresponds to I1 up to IP minus 1. And then in the last entry, when I take the inner product of the vector TI1 up to IP minus 1 with the vector EIP, I will be left with simply TI1 IP minus 1 IP, which is exactly what I have on the left hand side. Okay, so again I just use TI1 up to IP minus 1. So this vector inner product with EIP, this is giving me TI1 up to IP. Okay, so those two arrays, the arrays that I described on the left and the array on the right, are the same. And of course, on the right, I have a sum of d to the p minus 1 non-symmetric rank 1 tensors. So it's completely trivial that you can write an order p tensor into a sum of d to the p minus 1 rank 1 tensor. Now for the second fact, all I need to do is to show to you that a non-symmetric tensor, a non-symmetric rank 1 tensor, can be written as a sum of 2 to the p symmetric rank 1 tensors as far as the action on symmetric tensor is concerned. Okay, so now, second claim. Need to show that W1 times etc. times WP can be written as a sum of 2 to the p rank 1 symmetric tensors. Okay, and again, when I say can be written as, I mean can be written as in the sense of as far as the action on symmetric tensor is concerned. Okay, and what I mean by this is this equality. Okay, that you only look at t applied to x to the p. Okay, so here is the proof of this fact. It's a nice proof, I think. So it's a very simple probabilistic construction. So take psi1 up to psi p, IID random signs. And let's consider the expectation of the product for I equals 1 to p of psi I. So this is just a sign times the sum for I equals 1 to p of psi I wi, and this tensor p times. Okay, so let me explain this. You can think of it as I'm taking a random walk over this vector wi. Okay, so this is a sum for I equals 1 to p of psi I wi. And now this is going to be my symmetric tensor. I take this to the power p times, and I append to it a sign, either a -1 or +1, depending on the product for I equals 1 to p of the psi I. and I take the expectation of this. So this tensor is exactly a sum of 2 to the p rank 1 symmetric tensors. Okay, the expectation hide a sum over all, you know, signs for, so I have 2 to the p signs assignment for xi1 up to xi p. Now let's expand out what this is. So what is this? So this is the expectation. So I have my first product for I equals 1 to p. And now when I have this sum and I expand it power p times, what will I get? Well, I will get the product for I1 up to IP. Let me just think. I1 up to IP between 1 and p. Okay. So if you want, what is this tensor product, right? It's the first sum times the second times the same sum times the same sum, etc. So when I expand this out, what will I get? Well, I will get, I need to, sorry, it's a sum. It's not a product, it's a sum. Okay, I will take one element from the first sum, one element from the second sum, one element from the third sum, etc. So what is this? So this is xi I1 W I1 times, etc. times xi IP times WIP. This is exactly the same thing. Okay, I have taken one element from the first sum, one element from the second sum, etc., and I multiply all of those things. And in here I had the product of xi I. Now here is the miracle. Everything disappears in this expectation, except if in I1 up to IP I have exactly one element of each. Okay, so this is going to be equal to the sum over you know, over all permutation sigma, permutation of 1 through p. And what do I have? I just have, you know, W sigma 1 times etc. times W sigma p. And let me just verify that I'm not missing a factor here. I'm probably missing 1 over 2 to the p. Right. And that's it. Now you see this, now this tensor is equal to W1 times WP as far as action on symmetric tensors is concerned. Okay, it's the same thing. All right, so this shows to you that I can always write, you know, a non-symmetric rank 1 tensor into a sum of 2 to the p symmetric rank 1 tensor as far as you're concerned with the action on symmetric tensors. So that proves our second claim, okay, that you can always write it as a sum of symmetric rank 1 tensors as long as you have k equals 2 to the p times d to the p minus 1. Okay, very good. Okay, so now what I want to show to you is that the largest cross norm is not too much larger than the smallest cross norm. So this is lemma 2. And lemma 2 is going to be that the norm star, nuclear norm, is smaller than d to the p minus 1 times operator norm, norm of t. Okay, so let's see the proof of that. So for this proof, what I'm going to take is a decomposition into non-symmetric tensors that we had before. So it's a sum for I1 up to IP minus 1 between 1 and d of EI1, the I1 vector of the canonical basis, times EIP minus 1 times, you know, the vectors that I see in the slice I1 up to IP minus 1. So this is T I1 up to ip minus 1. And this is a vector when I leave the last coordinate unspecified. So the norm of t dual by the triangle inequality is going to be the sum smaller than the sum for I1 up to ip minus 1 between 1 and d of the norm star of this product. But the norm star is a cross norm, so by definition the norm of a rank 1 tensor is the product of the norm of the corresponding element. Now the norm of the canonical basis vectors is 1, so what I'm left with is just the norm, the Euclidean norm of t I1 up to ip minus 1 double dot. Euclidean norm of this. So now I can apply Cauchy-Schwarz, and what I get is this is smaller than square root of number of terms in this sum, which is d to the p minus 1, times the sum of those elements squared. But what is the sum of those elements squared? It's the sum of all the entries in the array square. So what I get is this is the Hilbert-Schmidt norm. So this is square root of d to the p minus 1 times the Hilbert-Schmidt norm of t. Now by duality, I will have the same reverse inequality for the dual norms. So by duality, the norm of t now is bigger than, let me just make sure that I get this right. The dual norm is bigger than 1 over square root d to the p minus 1 times the dual norm of the Hilbert-Schmidt norm, but the Hilbert-Schmidt norm is self-dual. So this is larger than the Hilbert-Schmidt norm, okay, which, again, this is larger than 1 over d to the p minus 1 times the norm star. So this concludes the proof. Okay, and now a last lemma very quickly that I want to give you is that the norm of t, the operate norm of t, again, is a supremum over, let's say, x1 up to xp unit norm of t applied to x1 times xp. And now all I want to tell you is that for symmetric tensor, in fact, you just need to take the supremum over a single unit vector. So for symmetric tensor, what is a symmetric tensor? A symmetric tensor is just so that, if I look at the entry I1 up to IP, it's the same as any permutation of the indices, okay? Or equivalently, it's a linear combination of symmetric rank 1 tensors. Okay, so for symmetric tensors, this is in fact the supremum over just x on the unit sphere of t applied to x to the p. Okay, and I won't prove this. You can easily do this by induction. Okay, very good. So now that we've seen the basics of tensor algebra, I'm going to tell you about some application of this to neural networks. So application to neural networks. Okay, so remember, what is a one hidden layer neural network? It's a function of the form sum of AL psi of WL dot X. Okay, for L equals 1 to K. So this is K neurons. Psi is a nonlinearity from R to R. The AL are the recombination weights in R, and the WL are directions in R. Okay. Now, what is the connection to tensors? Well, the connection to tensor is let's fix psi, the nonlinearity, to be a polynomial. Fix psi of t is a sum, let's say, for q equals 0 to p, a degree p polynomial of cq t to the q. So in this case, what is this? This becomes a sum for q equals 0 to p of cq, sum for L equals 1 to k of AL. And what do I get? I have WL dot X to the Q. But in our notation, what is this? This is nothing but the inner product between the symmetric rank 1 tensor WL tensor Q time times X tensor Q times. So now by linearity, I can rewrite this as the sum for q equals 0 to p of tq, a tensor of order q, applied to x to the q, where tq is nothing but cq times the sum for L equals 1 to k of AL WL to the q. Okay, so one hidden layer neural network with a polynomial nonlinearity is nothing but a tensor, a sum of tensors. Okay, applied to the corresponding embedding of x into x to the tensor power, the corresponding power. Okay, very good. So now let's see, let's go back to our law of robustness. So reminder, law of robustness. So what is the law of robustness setting? Oops, sorry about that. The law of robustness setting is like this. So given a data set, xi, yi, where the xi are on the sphere and the yi's are signed, -1 + 1, and let's say they are random, then the law of robustness tells us that any one hidden layer neural network with k neurons that fits the data. Okay, so on xi it outputs yi, must have Lipschitz constant at least square root n over k. So it cannot be too robust, and if you want it to be really robust, you need so it cannot be too robust, and if you want it to be robust, you need to have many neurons. Okay, so this is our law of robustness, and moreover, we conjecture that this is achievable, namely there exists a one hidden layer with k neurons that fits the data and has Lipschitz constant square root n over k. So let's see how this plays out when the nonlinearity psi is a polynomial, and we're going to fix simply, so for the rest of the lecture, psi of t is just going to be for the rest of the lecture, psi of t is just going to be t to the p, just the monomial t to the p, and it's easy to generalize to a full polynomial. Okay, so let's first see a polynomial construction, meaning an upper bound. How do you actually fit with this tensor network, a polynomial construction? Okay, so I want to find t, so find t, which is an order p tensor, so it's in Rd tensor p time, such that t applied to x to the p is equal to xi to the p is equal to y. So here is how I'm going to do it. So define omega. Instead of t, I'm going to define omega, and you will see why later. So define omega as this random tensor, the sum for I equals 1 to n of yi xi tensor p time. I claim that this tensor is a good data fitter. It gives you approximate data fit, and it will have a good Lipschitz constant. So first note that naively, this is a n neuron neural network, but by lemma 1 above, it is in fact a k neuron neural network with k. You can always take k less than 2 to the p d to the p minus 1. Okay, you remember this was the fact that you can always write a tensor as a sum of 2 to the p times d to the p minus 1 rank 1 symmetric tensor. So you can rewrite omega. In fact, there is a rewriting of omega into a smaller, more compact representation where instead of n, you have only k neurons where k is less than 2 to the p d to the p minus 1. Okay, and maybe you're wondering, is d to the p minus 1 less than n? Note n should be less than d to the p, right? This is what you can fit with a tensor network of order p, because you have only d to the p degrees of freedom, so you're not going to be able to fit more than d to the p equations. Okay, so in the maximal case, when n is like d to the p, then this representation into d to the p minus 1 neurons is indeed a smaller representation. Okay, so we know that k is less than d to the p minus 1 of order of this. So now let's see if this is a good data fitting strategy. So let's apply omega to xi to the p. What do we get? Okay, so we first get the term yi, which comes from applying xi to the p to xi to the p. Xi is a unit norm vector. And then what do we get? We get the sum for j equals 1 to n, j not equal to I, of yj times xi inner product with xj to the p. Okay, xi inner product with xj to the p, this is just the tensor xi to the p applied, inner product with the tensor xj to the p. And what is the order of this? Well, with high probability, this is going to be of order square root log n, because I need to do a union bound over the n data points, over d. Okay, so each of these sum n here is of order, let's forget about the log, 1 over square root d to the p, so 1 over d to the p over 2, and I sum with random sign. So I will have some kind of central limit theorem, which tells me that the order is square root of n. So this is going to be equal to yi plus something of order square root n over d to the p. So what do we see? We see that this is equal to yi plus a little o of 1 if d to the p is much larger than n. And remember that anyway we had the condition n needs to be less than d to the p, and now we had just the condition that n is much smaller than d to the p. Okay, some asymptotically smaller value. And in this case, indeed, omega is a good fit. Okay, it's equal to yi plus something a little o. So now it remains to estimate what is the Lipschitz constant. So what is the Lipschitz constant of omega? Well, what is the Lipschitz constant of omega? This is equivalent. It's easy to see, I didn't really explain, but this is equivalent to understanding what is the operator norm of omega. Okay, so what is the operator norm? By lemma 3 above, it's the supremum over all x unit norm of omega applied to x, which is a supremum over all x of the sum for I equals 1 to n of yi xi inner product with x to the p. Now, for fixed x, we said that this is of order square root n over d to the p. That's what we said before. But then uniformly on x, what's going to happen is that you will just have to do a union bound, okay, over the entire sphere, which you can do with an epsilon net argument you can discretize. So you will have square root n over d to the p times just a log factor, log of the size of the discretization, and the size of the discretization is like 2 to the d. So what you will get is square root n over d to the p minus 1. But now, here is the magic. What is square root n over d to the p minus 1? Remember that k, we always know that k is less than d to the p minus 1. So this thing is square root n over k, which is exactly what our law of robustness predicts. So in fact, tensor network interpolation gives you a matching construction for our law of robustness in the special case, where k is equal to d to the p minus 1, and n is of order d to the p. Okay, so we see that we can actually fit with tensor network and optimally in terms of Lipschitzness. Now, what I'm going to do next is I'm actually going to prove that this is optimal. Okay, so proof of the law. So the law again is that you cannot do better. Proof of the law for polynomial network. So say T is such that the inner product of T with xi to the p is equal to yi. Then what do we know? We know that in fact T correlates with the tensor omega that we just defined before. T times omega is equal to n. Okay, remember omega is just the sum of yi xi to the p. But now, what is this? This is what do we know about omega? We know how to control the operator norm of omega. So by Hölder's inequality is smaller than the operator norm of omega times the dual norm of T. So we know that this is larger than n. And we just proved that the operator norm of omega is smaller than square root n over d to the p minus 1 times the operator norm dual. Okay, so what we have is the dual operator norm of T is larger than square root n times square root d to the p minus 1. But now what do we care about? We care about the Lipschitz constant of T, which is the operator norm. So we know that the largest cross norm, the dual operator norm, is larger than square root n times square root d p minus 1. But remember lemma 2. Lemma 2 tells us that the smallest cross norm is not too much smaller than the largest cross norm. Namely, it's larger than, well, square root d to the p minus 1. Sorry. It's larger than 1 over d to the p minus 1 times the norm of dual, which is larger than square root n over d to the p minus 1. This proves the law of robustness because this is equal to square root n over k if k is the largest possible. Okay, so this proves the law of robustness in a particular regime for polynomial network. And let me just conclude that by a note, a remark. For p equals 2, lemma 2, in fact, is more precise. You get the operator norm is larger than 1 over k times the dual operator norm. This is again just because if you have a rank k matrix, then you have only k non-zero singular values. So the dual operator norm, the nuclear norm, the sum of the singular value is less than k times the max of those. So in this case, you actually get that the Lipschitz constant of a neural network is larger than, so in this case, what do you get? You get square root n over k times square root d over k. So you see that low rank does not match the law. So it's provably suboptimal to use a low rank structure, at least for matrices. And we have no idea if this is true with higher order tensors. It would be very, very interesting to know for higher order tensors, but it turns out that this inequality for rank k tensor is not true. So you will have to use a different proof. Okay, I will conclude here. I hope this convinces you that, you know, tensor calculus is interesting, not too difficult, and relevant for neural networks. And I hope somebody can, you know, prove or understand what happens for low-rank tensors in our law of robustness conjectures. Okay, that will be it. Thank you.